Testing, can you hear me? Hello, can you hear me? Testing my mic again. Hello, everyone. So, I'm going to be reading the physics book again. Hold on. I think this looks better. And wait, wait, let me just change a few things. I should have done this off stream, but I guess this is good enough. Anyways, um, so last video I learned about work in kinetic energy. This stream I will learn about potential energy and the conservation of energy. Let's just start with 8.1. In work, we saw that the work done on an object by a constant gravitational force near the surface of Earth over any displacement is a function only of the difference in positions of the endpoints of the displacement. This property allows us to define a different kind of energy for the system than its kinetic energy, which is called potential energy. We consider various properties and types of potential energy in the following subsections. In motion in two and three dimensions, we analyze the motion of a projectile, like kicking a ball in figure 4 in figure 8.2. For this example, let's ignore friction and air resistance and begin the analysis immediately after the kick. At the start of the projectile motion of the ball, as the football rises, the work done by the gravitational force on the ball is negative because the ball's displacement is positive vertically and force due to gravity is negative vertically. He also noted that the ball slowed down until it reaches its highest point, thereby decreasing the ball's kinetic energy. This loss in kinetic energy translates to a gain in gravitational potential energy of the football Earth system. As the football falls towards Earth, the work done on the football is now positive because the displacement and gravitational force both point vertically downward. The ball also speeds up, which indicates an increase in kinetic energy. Therefore, the energy is converted from gravitational potential energy back into kinetic energy. So, ball ascends, kinetic energy decreases, potential energy increases. At highest point, kinetic energy is minimum, potential energy is maximum. Ball descends, kinetic energy increases, and potential energy decreases. Based on this scenario, we can find the difference of potential energy from point A to point B as a negative of the work done. This formula explicitly states a potential energy difference, not just an absolute potential energy. Therefore, we need to define a potential energy at a given position in such a way as to state standard values of a potential energy on their own, rather than potential energy differences. We do this by rewriting the potential energy function in terms of an arbitrary constant. Okay, the choice of the potential energy at the starting location uh, R0 is made out of convenience in the given problem. Most importantly, whatever choice is made should be stated and kept consistent throughout the given problem. There are some well accepted choices for initial potential energy. For example, the lowest height in a problem is usually defined as zero potential energy. And if an object is in space, the farthest point away from the system is often defined as zero potential energy. Then the potential energy with respect to zero at R0 is just UR. So long as there is no friction or air resistance, the change in kinetic energy of the football equals negative of the change in gravitational potential energy of the football. This can be generalized to any potential energy. Let's look at a specific example, choosing zero potential energy for gravitational potential energy at convenient points. A particle moves along the x-axis under the action of a force given by F is equal to minus ax squared, where a is 3 newtons per meter square. What is the wait, what is the difference in potential energy as it moves from xa1 to xb2? What is the particle's potential energy at x is equal to 1 with respect to a given zero point 0.5 joule of potential energy at x is equal to 0? So force, we have example 8.1. Force is minus ax squared. We need the difference in potential energy. From A to B is equal to negative work done from A to B. Work done by the force. Let's say this function is with f of x from A, which is 1, sorry, force. It's this, right? Or from A to B. If I remember correctly, it was this, right? We have 3, but I will take the 3 outside from 1 to 2. This feels correct. This and this would cancel, so we are left with 2 cubed minus 1 cubed, which is 1. We have 8 minus 1, so minus 7. So then this is positive 7. Wait, yeah, 7 joules. What is the particle's potential energy at x is equal to 1 with respect to a given with respect to a given 0.5 joule of potential energy at x is equal to 0? So we have, so now we need it from 0 to 1, right? This is from 1 to 2. This is A. As for B, we have work from A to B. We have the indefinite integral of this. We have negative 3. No, wait. Plus C. So U B is equal to minus B cube plus C. U0 is equal to 0.5 joules. So that means uh, difference from, so for part B we have, getting confused. We need from 0 to 1, right? From 0 to 1, it's B minus A. So B minus A is negative 1. How can it be negative 1? Or they aren't asking for the difference. They're asking the potential energy at 1. So they're not asking for the difference. They're asking for this cubed plus 0.5. Mm. But here's the problem. No, this is positive 3. This was never negative. And this is 1.5 joules. Also, this was positive. 3 and 3 cancel. 2, you have 8. Minus 1, 7. And we have 3 times 7, right? But the thing is, what happens to the minus though? Oh, the equation has a minus in it. No, I was correct about before. The equation has a minus in it. But then what about if the equation has minus in it, then there would be a minus here, here, here. Then this should be minus 0.5. Why is it a positive? Shouldn't it be a negative? It's negative of work. Okay, if it's negative of work, then yeah, this should be positive. In general, a system of interest could consist of several particles. The difference in the potential energy of the system is the negative of the work done by gravitational or elastic forces, which, as we will see in the next section, are conservative forces. The potential energy difference depends on the initial and final position of the particles and on some parameters, the characteristic that in the that, on some parameters that characterize the interaction. It is important to remember that potential energy is a property of the interaction between objects in a chosen system. and not just a property of each object. For each type of interaction present in a system, you can label a corresponding type of potential energy. The total potential energy of the system is the sum of the potential energies of all the types. Let's look at some specific examples of types of potential energy discussed in work. First, we consider each of these forces when acting separately, uh, and then when both act together. The system of interest consists of our planet Earth and one or more particles near its surface, or bodies small enough to be considered as particle compared to Earth. Gravitational force on each particle is just its weight mg near the surface of the Earth acting vertically down. According to Newton's third law, each particle exerts a force on Earth of equal magnitude but in the opposite direction. The work done on a body by Earth's uniform gravitational force near its surface, dependent on the mass of the body, the acceleration due to gravity, and the difference in height of the body traversed, as given by equation 7.4. By definition, this work is negative of the difference in gravitational potential energy. So that difference is, we have difference negative of work. And see from this equation that the gravitational potential energy function near Earth's surface is mgy plus constant. He saw that work done on an object by constant gravitational force near the surface of the Earth or any displacement is a function only of the difference in positions of the endpoints of the displacement. This property allows us to define a different kind of energy for the system than its kinetic energy, which is called potential energy. Elastic potential energy in work, we saw that the work done by a perfectly elastic spring in one dimension depends only on the spring constant and the squares of the displacement from the unstretched position, as given in equation 7.5. This work involves only the properties of a Hooke's law interaction and not the properties of real springs and whatever objects are attached to them. Therefore, we can define the difference of elastic potential energy for a spring force as a negative of the work done by the spring force in this equation. Therefore, we consider systems that embody this type of force. Thus, delta U is minus WAB. The object travels from point A to point B. Potential energy function corresponding to this difference is, if the spring force is the only force acting, it is simplest to take zero of potential energy at x is equal to 0 when the spring is at its unstretched length. Then the constant in equation 8.7 is 0. All right. A simple system embodying both gravitational and elastic types of potential energy is a one-dimensional vertical mass spring. This consists of a massive particle block hung from one end of a perfectly elastic massless spring, the other end of which is fixed as illustrated in figure 8.4. A vertical mass spring system with the positive y-axis pointing upwards. Mass is initially at an unstretched spring length, point A, then it is released, expanding past point B to point C where it comes to a stop. So then we have the y position and minus 2 mg over k. A block weighing 1.2 Newton is hung from a spring with a spring constant of 6 Newton meter. What is the maximum expansion of the spring as seen at point C? Example 8.4. A block weighing 1.2 newtons is hung from a spring. 1.2 newtons. Gravitational force facing downwards is 1.2 newtons m 9.81. I'll just write G, and then the force here for the spring is equal to Ky K delta Y. Wait, Ky Y is the dis- displacement from the starting position. K is 6 Newton meter. So the y distance is 6 Newton meter. No, wait. Force divided by K is y. So force is 1.2 6 G. Mg over K. Mg over K. But why 2 though? Ground is a suitable choice. No, wait, this force is the force the string is pushing back on. This is not the gravitational. Yeah. This is incorrect. Force of the spring is Ky. I'll just write 6. Now the potential energy is the distance. Wait, force is constant. Y C. Gravitational force for all for this distance. And the work done is half KY C square. K. The negative of this is KYC square is YC, which is minus 2 mg over K. But the thing is, I don't know the mass, but we do know that the force, gravitational force is 1.2, right? So we can just use this. Hold on, I should also open this mouse. We have minus 2 over 6, minus 2 over 6, 1.2, minus 0.4. So the negative 50 is the downward one, right? So minus 0.4 meters. It comes to a halt over there. What is the total potential energy at point B halfway between A and C? Total potential energy at point B between A and C. Total potential energy. What do they mean by total potential energy? The difference in energy makes sense. So this is A. Now I'm going to do B. So we have, what did they do? Position of YB is half the position at YC. Or YB, they forgot to subscript it. Is YC divided by 2 is minus mg over K. What do they mean by total potential energy? Don't we need like a 0 point? If the spring force is the only force acting, it is simplest to take 0 as the potential energy at x is equal to 0. When the spring is at its unstretched length, then the constant is 0. You can choose the value of the constant as described in the discussion of equation 8.2. However, for solving most problems, the most convenient constant is to choose is 0 for when y is equal to 0, which is the lowest vertical position in the problem. Okay. The mass of the block is the weight divided. They ask for the mass. They ask for the speed. Kinetic energy at point B is therefore 0.1 joules because the total energy is 0. Therefore, the speed of the block at point B is equal to A is equal to half mv square. In the like, I still don't have a clear understanding of potential energy or like what energy is. In the interactions we considered in potential energy and conservation of energy, any transition between kinetic and potential energy did not change the total energy of the system. This was path independent, meaning that we can start and stop at any 2 points in the problem. And the total energy of the system, kinetic plus potential, at these points are equal to each other. This is characteristic of conservation force, conservative force. We deal with conservative forces in the preceding section, such as gravitational force and spring force. In comparing the motion of the football in figure 8.2, the total energy of the system never changes, even though the gravitational potential energy of the football increases as the ball rises relative to the ground and falls back to the initial gravitational potential energy when the football player catches the ball. Non conservative forces and the work that they do are path dependent. Dissis- Dissipative forces such as friction or resistance, for example, are non conservative. These forces take energy away from the system as the system progresses, energy that you can't get back. Push pull forces are also generally non conservative. Imagine pushing a merry-go-round. Total work done in returning to the starting point depends on how many revolutions are completed, and therefore the total energy at that location is not constant. The work done by a conservative force is independent of the path. In other words, the work done by a conservative force is the same for any path connecting 2 points. So we have work done from A to B. Uh, Conservative force dr equal to work done by path 2. The work done by non-conservative force depends on the path taken. Equality of force is conservative if the work it does around any closed path is 0. In equation 8.9, okay, I haven't done this in the calculus section, but I think I should complete the calculus book before going any further, maybe. Use the notation of a circle in the middle of the integral sign for a line integral over a closed path, a notation found in most physics and engineering texts. Equation 8.8 and 8.9 are equivalent because any closed path is the sum of two paths. The first going from A to B, the second going from B to A. The work done going along a path from B to A is the negative of the work done going along the same path from A to B, where A and B are any 2 points on the closed path. You might ask how we go about proving whether or not force is conservative, since the definitions involve any and all paths from A to B or any and all closed paths. But to do the integral for the work, you have to choose a particular path. One answer is that work done is independent of path if the infinitesimal work is an exact differential. The way the net, the way the infinitesimal net work was equal to the exact differential of the kinetic energy. So infinitesimal work done It's mv times dv, which is d half mv squared. When we derive the work energy theorem in work, when we derive the work energy theorem in work energy theorem, there are mathematical conditions that you can use to test whether the infinitesimal work done by a force is an exact differential and the force is conservative. These conditions only involve differentiation and are thus relatively easy to apply. In two dimensions, the condition for f times dr is equal to fx dx plus fy dy to be an exact differential. So to be an exact differential is okay. You may recall that the work done by a force in example 7.4 dependent on the path uh, for that force is f of x is 5y and f of y is 10x. Therefore, d f over dy is 5, which is not equal to d uh, f of fy over dx. Which indicates it is a non-conservative force. Can you see what you could change to make it a conservative force? Which of the following two-dimensional forces are conservative and which are not? Assume any pair constants with appropriate units. We have A and we have B. We have this over here. Okay, let's do example 8.5. This part is new to me. I should have finished the calculus book before starting physics. So we have AXY cube. We have that. Well, let's draw it like a vector. AYX cube. Now, f in the partial derivative with respect to x is a y cubed a x cubed, and then derivative of this with respect to y 0, which is the same if we switch the variables. So for a we have um wait, hold on, what's happening? Oh no, this is not partial derivative. This is force in the x direction and force in the y direction. Okay, okay. I got it. This is wrong then. So force in the x direction is this. Right, right. We have ax as constant, and then we have 3y square. And then we have this time ay as constant for this, and then we have 3x square. So non-conservative. Now let's try b. So a is multiplying with the entire thing. Y square over x. 2y ln x. It's ln b over x over b. Okay. We have this x part with respect to y. And now this over here is 2y ln of x minus 2y ln of b. We can take 2y out because they're constant here. And then this will give ln of x is 1 over x, right? No. Yeah. And this is 0. And then we have a. So this versus conservative. For leaving this section, we note that non-conservative forces do not have potential energy associated with them. There's always a conservative force associated with every potential energy. We have seen that potential energy is defined in relation to work done by conservative forces. This relation, equation 8.1, involved an integral for the work. Starting with the force and displacement, you integrate it to get the work and you change in potential energy. However, integration is the inverse operation of differentiation. You could equally well have started with the potential energy and taken its derivative. With respect to displacement to get the force, the infinitesimal increment of potential energy is the dot product of the force and infinitesimal displacement. So dU is equal to minus F times dL, which is equal to minus FL dL. Here we choose to represent the displacement in an arbitrary direction by dn so as to not be restricted to any particular coordinate direction. We also express the dot products in terms of the magnitude of the infinitesimal displacement and the component of the force and its direction. Both these quantities are scalars, so you can divide by dl to get this. This equation gives the relation between force and potential energy associated with it. In other words, the component of conservative force in a particular direction equals the negative of the direction of the derivative of the corresponding potential energy with respect to the displacement in that direction. For one-dimensional motion, say along the x-axis, give the entire vector force. In two dimension, we have the force as a vector in the x component I plus y component j. So partial derivative with respect to x minus partial derivative with respect to y. Oh, from this equation. And this equation, you can see why equation 8.11 is the condition for the work to be an exact differential in terms of the derivatives of the components of the first. In general, partial derivative notation is used if a function has many variables in it. The derivative is taken only of the variable the partial derivative specifies. The other variables are held constant. In three dimensions, you add another term for the z component, and the result is that the force is the negative of the gradient of the potential energy. However, we won't be looking at three-dimensional examples just yet. The potential energy for a particle undergoing one-dimensional motion along the x-axis is 1 over 4 cx to the power of 4, where c is equal to 8 Newton per meter cube. Its total energy at x is equal to 0 2 joules. It is not subject to any non-conservative forces. Find the positions where its kinetic energy is 0 and the forces at those positions. Potential energy for a particle undergoing one-dimensional motion along the x-axis. So this is exercise example 8.6. 1 over 4 cx 4 at 0, it is 2 joules. C is equal to 8. So we need to find, let's call it position A. Position A minus position 0 is equal to 0 joules. It is not subject to any non-conservative forces. Hold on. X is equal to 0 is 2 joules. If I plug in 0 over here, I get 0, right? Its total energy at x is equal to 0 is 2 joules. And we need to find the positions where kinetic energy is 0. But I don't understand this though. Shouldn't by this equation position be 0? Total energy of the system of 2 joules equals the quad- quadratic elastic energy as given in the problem. So what I was gonna do is like something like this. This to the power of 4. A is equal to plus minus 1. I would have most likely said just 1 meters. Uh, the forces at those positions. The force is equal to minus du over dl is equal to Ex cube. The position is plus or minus 1. We have 8 times 1, so positive 8 newtons, plus or minus 8. It's just right I. In this section, we elaborate and extend the result we derived in potential energy of a system, where we rewrote work energy theorem in terms of change in kinetic and potential energies of a particle. This will lead us to a discussion of the important principle of the conservation of mechanical energy as we continue to examine other topics in physics. In later chapters of this book, you will see how this conservation law is generalized to encompass other types of energy and energy transfers. The last section of this chapter provides a preview. The terms conservative quantity and conservation law have specific scientific meanings in physics, yet different from the which are different from the everyday meanings associated with the use of these words. Everyday usage, you could conserve water by not using it, or by at least less of it, or by reusing it. Water is composed of molecules consisting of two atoms of hydrogen and one of oxygen. Bring these atoms together to form a molecule and you create water. Disassociate the atoms in such a molecule and you destroy water. However, in scientific usage, you conserved quantity for a system. A conserved quantity for a system stays constant. Changes by definite amount that is transferred to other systems or is converted into other forms of that quantity. Conserved quantity is, in the scientific sense, can be transformed but not strictly created or destroyed. Thus, there is no physical law of conservation of water. We first consider a system with a single particle or object returning to our development of equation 8.2. Recall that we first separated all the forces acting on a particle into conservative and non-conservative types and wrote that the work done by each type of force as a separate term in the work energy theorem. We then replaced the work done by the conservative force or by the charge in the potential energy of a part of the particle, combining it with the change in the particle's kinetic energy to get equation 8.2. Now we write this equation without the middle step and define the sum of the kinetic and potential energies. K plus U is equal to E to be the mechanical energy of the particle. The mechanical energy of a particle stays constant unless forces outside the system or non-conservative forces do work on it. In which case, the changes in mechanical energy is equal to the work done by non-consecutive conservative forces. This statement expresses the concept of energy conservation for classical particles as long as there is no non-conservative work. Recall that a classical particle is just a point mass, is non-relativistic, and obeys Newton's laws of motion in relativity. We see that the conservative conservation of energy still applies to a non-classical particle. But for that to happen, we have to make a slight adjustment to the definition of energy. It is sometimes convenient to separate the case where work done by non-conservative forces is zero, either because no such forces are presumed present, or like the normal force, they do zero work when the motion is parallel to the surface. Then we have work done by non-conservative forces, just zero. This case, the conservation of mechanical energy can be expressed as follows. The mechanical energy of a particle does not change if all the non-conservative forces that may act on it do no work. Understand the concept of energy conservation is the important thing, not the particular equation you use to express it. In these examples, we were able to use conservation energy to calculate the speed of a particle just at particular points in its motion. But the method of analyzing particle motion starting from energy conservation is more powerful than that. More advanced treatments of the theory of mechanics allow you to calculate the full time dependence of a particle's motion for a given potential energy. In fact, it is often the case that a better model for particle position is provided by the form of its kinetic energy and potential energies rather than an equation for forces acting on it. We can illustrate some of the simplest features of this energy based approach by considering a particle in a one dimensional motion with potential energy, no non conservative interactions present. Equation 8.12 and the definition of velocity required. You have this, the velocity dx over dt. Separate the x and t, separate the variables x and t, and integrate from an initial time t is equal to 0 to an arbitrary time to get. If you can do the integral in equation 8.14, then you can solve for x as a function of t. Use the potential energy in equation 8.14 to find the position x of a particle as a function of time t. They have this, they have integrating from, okay, which is equal to, hold on, let me do this my own. Example 8.9. T x x naught to to e minus ux, whatever. So we are integrating with respect to x. No, wait, this is dx. Hold on, how do we do that then? Use the potential energy ux is equal to e x over x naught for e more than 0. What? Since we know how the potential energy changes as a function of x, we can substitute for u in equation 8.14 and integrate. E is a function, right? What is E? Or E is this multiplying? Okay, I have no clue what's going on in here. The results in an expression of x as a function of time with constants of energy, mass, and initial position. Minus E x over x naught. Now, I don't know what's happening. Do we take E out? Is this multiplying? Because I thought this was like a function. Do E and then we have x naught over x naught. And then they took the x naught out. And then they did something like this. And then they integrated with respect to x. Okay, and they got this. Okay, well, they took the constant out, got this, and they ended up with this. X naught minus half e over mx naught t square. Often you can get a good deal of useful information about the dynamic behavior of mechanical system just by interpreting a graph for its potential energy as a function of position, called the potential energy diagram. This is most easily accomplished for a one-dimensional system whose potential energy can be plotted in one two-dimensional graph. For example, ux versus x on a piece of paper or a computer program. For a system whose motion is in more than one dimension, the motion needs to be studied in three-dimensional space. We will simplify our procedure for one-dimensional motion only. First, let's look at an object freely falling vertically near the surface of Earth. In the absence of air resistance, the mechanical energy of the object is conserved, and the potential energy with respect to zero at ground level, which is a straight line through the origin with slope mg. In the graph shown in figure 8.10, the x-axis is the height above the ground y, and the y-axis is the object's energy. Energy k plus u constant. You have this. The line at energy E represents the constant mechanical energy of the object, whereas the kinetic and potential energies Ka and Ua are indicated at a particular height Ya. You can see how the total energy is divided between kinetic and potential energy as the object's height changes. Since kinetic energy can never be negative, there is a maximum potential energy and a maximum height, which an object with a given total potential energy cannot exceed. If we use gravitational potential energy reference of point of 0 at y naught, we can rewrite the gravitational potential energy U as mgy, solving y results in, yep, this, and E over mg is y max. You note in this expression that the quantity of the total energy divided by the weight is located at the maximum height of the particle, or y max. At the maximum height, the kinetic energy and the are zero. So if the objects were initially traveling upwards, the velocity would go through zero there. The Ymax would be turning Ymax, and Ymax would be a turning point in the motion. The ground level, the potential energy is zero, and kinetic energy and the speed are maximum. The maximum speed plus or minus v naught gives the initial velocity necessary to reach Ymax. Maximum height and minus v naught represents the final velocity after falling from y max. Okay, they have something similar for the spring. X max is plus minus root 2 e over k. And u is equal to k. U is equal to e is the turning point. In this chapter, we have studied energy. We learned that energy can take different forms and can be transferred from one form to another. You will find that energy is discussed in many everyday as well as scientific contexts because it is involved in all physical processes. It will become apparent that many situations are best understood or most easily conceptualized by considering energy. Like I want to see how like the concept of energy was evolved through the history of physics. I think that would explain a lot. So far, no experimental results have contradicted the conservation of energy. In fact, whenever measurements have appeared to conflict with energy conservation, new forms of energy have been discovered or recognized in accordance with this principle. Atoms are molecules inside all objects are in random motion. The internal kinetic energy from these atom motions is called thermal energy because it is related to the temperature of the object. Electrical energy is a common form that is converted to many other forms and does work in a wide range of practical situations. Fuels such as gasoline and food have chemical energy, which is a potential energy arising from the molecular structure. Chemical energy can be converted into thermal energy by reactions like oxidation. Light is just one kind of electromagnetic radiation or radiant energy, which also includes radio, infrared, ultraviolet, X rays, and gamma rays. Nuclear energy comes from reactions and processes to convert measurable amount of mass into energy. Nuclear energy is transformed into radiant energy in the sun, into thermal energy in the boilers of nuclear plants, and then into electrical energy in generators of power plants. These and all forms of energy can be transformed into one another and to a certain degree can be converted into mechanical work. Energy is an important element at all levels of society. We live in an very interdependent world. Access to adequate and reliable energy resources is crucial for economic growth and for maintaining the quality of our lives. Principal energy resources used in the world are shown in figure 8.14. So world energy consumption by source, the percentage of renewables is increasing, accounting for 19% in 2012. The principal energy resources used in the world are shown in figure 8.4. The figure distinguishes between two major types of energy sources, renewable and non-renewable. Further divides each type into a few more specific kinds. Renewable sources are energy sources that are replenished through naturally occurring ongoing processes on a timescale that is much shorter than the anticipated lifetime of the civilization using the source. Non-renewable sources are depleted once some of the energy they contain is extracted and converted into other kinds of energy. The natural process by which non-renewable sources are formed typically take place over geological timescales. So this is renewable, this is fossil fuels, and this is nuclear. Our most important non-renewable energy sources are fossil fuels such as coal, petroleum, and natural gas. These account for about 81% of world's energy consumption as shown in the figure. Burning fossil fuels creates chemical reactions that transform potential energy in a molecular structure of the reactants to thermal energy in products. Thermal energy can be used to heat buildings or to operate steam-driven machinery. Internal combustion and jet engines convert some of the energy of rapidly expanding gases released from burning gasoline into mechanical work. Electrical power generation is mostly derived from transferring energy in expanding steam via turbines into mechanical work, which rotates coils of wire in magnetic fields to generate electricity. Nuclear energy is the other non-renewable source shown in Figure 8.14 and supplies about 3% of the world's consumption. Nuclear reactions release energy by transforming potential energy in the structure of nuclei into thermal energy, analogous to energy release in chemical reactions. An unfortunate byproduct of relying on energy produced by combustion of fossil fuels is the release of carbon dioxide into the atmosphere and its contribution to global warming. Nuclear energy poses environmental problems as well, including the safety and disposal of nuclear waste. Besides these important consequences, reserves of new renewable sources of energy are limited, and given the rapidly growing rate of the world energy consumption, may not last for more than a few hundred years. Considerable effort is going on to develop and expand the use of renewable sources of energy, involving a significant percentage of the world's physicists and engineers. Yeah, I will just, since energy in an isolated system is not destroyed, created, or generated, you might wonder why we need to be concerned about our energy resources, since energy is a conserved quantity. Problem is that the final result of most energy transformation is waste heat, that is, work that has been degraded in the energy transformation. We will discuss this idea in more detail in the chapters of thermodynamics. Right, then I will end the stream here. Uh, yeah, I will need to read more about the history of the ideas of energy. And next stream, I will study the next chapter. Right, then I will see you guys next time. Bye.